This is a little reminder on horizontal asymptotes on rational functions. You covered this in pre-cal. We're doing exactly what you did in pre-cal. The only difference is we're putting LIM in front of the problem. So when you were in pre-cal, you would analyze functions like this, imagining what is happening to that function as you went toward positive infinity, or what's happening to that function as you went towards negative infinity. And you use a certain amount of just math logic to reason out what's happening. For simplicity's sake, I'm just going to write kind of a two-part limit. This is not good notation, but this is what you get today. So the first attempt at evaluating a limit is always direct substitution. And when you do so, we find that the limit has this indeterminate quantity, infinity over infinity. So the rule is fiddle with the algebra and try again. So when we are applying limits to values like plus or minus infinity, we have to recognize that the terms of, say, an x squared term is infinitely larger than those other terms in that numerator, because infinity squared means an infinite number of infinites, and 3 infinites, yeah, it's much smaller by comparison. So one of the things we're able to do, and this is only if you're substituting extremely large values, negative infinity, positive infinity, we can ignore all of the terms that sort of get washed out by the value of infinity. So we do something that's kind of like this. We say, okay, all those other terms we don't care about because the x squared when we're evaluating at infinity is much greater than anything else. That's going to be what we call fiddling with the algebra when you're taking limits at infinity. Now, even so, we have to try direct substitution again, and what do we get? We get the same indeterminate form, infinity over infinity. So our rule is fiddle with the algebra and try again. So this time when we look back at the algebra, you can see that the x squared on top, x squared down below, if we were just treating it algebraically, those would go away, leaving us with 1. And in fact, that's the limit. Now, what does that mean to us graphically, that the limit as x approaches infinity is 1? That means if we're going in this direction, the farther and farther we go to the right, we would get closer and closer and closer to y equals 1. So this is the way that we recognize that there's a horizontal asymptote at y equals 1 whenever this limit is evaluated at positive infinity. Now, we can also go back and see what the function is doing as we approach negative infinity. So when we imagine substituting in negative infinity, all the same logic that we used previously to ignore those terms still applies. We can also see that this is going to be an indeterminate negative infinity, and now we have to evaluate that. Well, once again, when you cancel, you get positive 1. Therefore, even as x is approaching negative infinity, the function is approaching the asymptote. So that gives us some information about the function, but if you're wanting to kind of sketch the function, you need a little bit more information, and that information is readily available. You remember in algebra that finding the intercepts, the y and x intercepts, can be extremely helpful. So in this case, let's find the y-intercept. Substitute in x equals 0, and then we get y is equal to 2. So that gives us a point on the curve now. So now we're in at least a good enough situation that we could sketch something that is similar or closely or close to the actual function. Now, once again, we don't know that the function looks exactly like this, but I do know at least that for part of the time that function is above the horizontal asymptote y equals 1, and then at both positive and negative infinity, the function is approaching y equals positive 1. Now, is it possible that the function also was below the asymptote? Absolutely. You know, there can be functions that do things like that, and so it still meets that condition of having an intercept at y equals 2 and still being asymptotic to that asymptote y equals 1. So once again, when we look at this function, if we want to know what the endpoint behavior of the function is, we will turn it into a limit, evaluate it at positive infinity and negative infinity. It's readily apparent that this limit is going to go to infinity over infinity when we substitute in positive infinity. So we already know we're going to have to piddle with the algebra. And the first thing to piddle, let's ignore those plus 1s because they're so minuscule compared to the actual substitutions of infinity. Well, we still have that problem. If we evaluate it, it's still infinity over infinity. So we have to do some more algebra. And when we do more algebra, we recognize, we recognize that we can cancel out an x. And now whenever we make our substitution, we would have positive infinity down at x, negative 1 here. So that's going to trend toward negative 0. And what does that look like on the graph? Well, that tells me that it's going to be horizontally asymptotic to the x-axis, but it's going to be below the x-axis as it approaches positive infinity. When you do the limit for negative infinity, you recognize that exactly the same algebra is going to occur, except that you'll be evaluating this at negative infinity. Well, that gives you a negative 1 over negative infinity, which means this one is trending toward positive 0. So as x approaches negative infinity, we know that the function is going to be above the x-axis. And now if we can just find a point, maybe even 2 if we wanted to graph this thing, we're on our way. Now let me make a note. We have modified that function for the purposes of taking a limit. The function that we have listed here, x over x squared, that's not equivalent to the function that we were actually given. This is called the power function that we're seeing in the parentheses. So when it comes to actually computing anything about the function, we have to take ourselves right back to the actual function and do our substitutions right there. It should be really readily apparent that if we substitute in x equals 0, y is going to be equal to 1. So at this point, we know a little bit about the function. We know about the horizontal asymptotes, and we know what the y-intercept is. But maybe we could find out a little more pretty easily, because this side of the function obviously is going to be crossing the x-axis. So one of the easiest things to do in a problem like this is just find an easy value to substitute. And what's easier than 0? 1. So we see that f of 1 is 0 over 2, or it's 0. So that means we know that the function here is crossing the x-axis at x equals 1. And let's go to the other side and check out x equals negative. So f of negative 1 is 1. That means that there must be a point right here at x equals negative 1. Now that would have the same value as the function did at the y-intercept. So at first that might seem a little bit peculiar to you, but functions do a lot of interesting things, and I'm not going to graph it, but I suspect here's what's happening when we put all the bits and pieces together. So I suspect something is going on like this. Could be wrong, but even so, even if this is not the actual graph, we did gather enough information about the graph that at the very least, if we were asked to identify a sketch of that graph, we'd be able to choose it from among others. So this will be our last example, and I picked this one because I can see it's a little bit tricky, which will be interesting. So the first order of business is, we all know that we're going to treat this as a limit in order to determine the end behavior, or the limit as x approaches plus or minus infinity. So by now, you're probably looking at these and you can see really quickly, okay, the only terms that I really have to care about whenever we're substituting in values like infinity would be those two terms. You can see the algebra coming along, and you can recognize, aha, there's going to be an asymptote at y equals negative. So because of the square, then it wouldn't matter whether we were substituting positive infinity or negative infinity. The value would always be approaching negative 2, so that means that the function's approaching negative 2 on both ends. So just, sort of generically, if we were trying to determine the y-intercept, and when we substitute 0 into all of those terms, we get a y-intercept of 5/2. So up here, 5/2, we'd presume, oh yeah, the function must be doing something like this. Or something, who cares, right? Except that there's something interesting and tricky here. Anytime we have a denominator, there's some chance that that denominator will be equal to 0. And if it is, then the function's either going to have a whole or a vertical asymptote. And so when we look at this problem, it may not be apparent at first, but if you factor that denominator, it is a quadratic trinomial after all, and we see that there are two values of x for which the denominator could be equal to 0. Now let's look in the numerator and see if we can see those factors anywhere in the numerator, and I don't see either of those factors, so that means this is not a whole, it's actually going to be a vertical asymptote. So our initial notion about the shape of the function is obviously quite different, because at x equals negative 2, there is a vertical asymptote, and at x equals 1, there's another vertical asymptote. So this function is doing something quite different than the others that we've seen. Now we can go ahead and use that intercept of y equals 5/2 and see if we can determine what this function is doing. Here's some of the possibilities. The function could be doing that. The function could be doing that. The function could be doing that. Or the function could be doing that. So in order to know what the function is doing around those vertical asymptotes, we're going to have to use left-hand and right-hand limits to figure that out. Now, I'm going to leave the function in its factored form, because when it comes to determining the sign of something, it's a lot easier to determine the sign on terms like that than the trinomial that we had earlier. So there will be 1, 2, 3, and 4 one-sided limits that we'll use to decide what the function's behavior is like around those vertical asymptotes. Now I'm going to use this really simplified form over here. I'm not going to rewrite the function over and over, but let's just look at the signs of these possibilities. We know that the function is going toward either positive or negative infinity. So all we have to do is look at the terms in the problem and determine whether it's positive or negative. If it's negative, then we know it's going toward negative infinity. If it's positive, then it's going toward positive infinity. So let's think about this. If we were substituting x approaching 2 from the left, this term would be positive. The negative 2, of course, just comes along. X plus 2, that would be slightly negative. And then finally, x minus 1, that would definitely be negative. So whenever we look at this, we say, aha, negative, 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 then that means the value of the limit is negative. And that tells us what the function's doing. It's going down toward negative infinity, to the left of the negative 2 asymptote. So let's check out the others. So now if we analyze values just to the right of x equals negative 2, we'll do the same thing. Well, the numerator would still be positive. The negative 2 is still negative. Now that x plus 2, since we're a little bit to the right of negative 2, then that's going to be a positive. And then finally, x minus 1 is obviously going to be negative. So we have negative, negative, which gives us positive. So what does that tell us? The function is going toward positive infinity on that side of the asymptote. Now, what does that look like on the graph? Well, since we know that the y-intercept is at 5/2, then I'm almost certain that the function does something like that. I can't imagine the function doing anything but that. So let's look at the others. So we'll next look at the limit just to the left of x equals 1. And what's that going to be? Well, we can see, of course, the numerator is going to be positive. The negative 2, of course, is negative. X plus 2 is going to be positive, and x minus 1 is going to be positive or negative. And it's negative because think of what we're doing. X is not equal to 1. X is a bit smaller than 1. So that becomes a negative quantity. And so now when we analyze that, that means that on that side of the asymptote, the function is positive, meaning it must be going toward positive infinity. So what does that look like on a graph? Well, I'm just turning around and heading right back up. So the last of the limits is going to be the limit as x approaches positive 1 from the right. And of course, the numerator is going to be positive. I put 5 there, by the way. We've got the negative 2. Then x plus 2 is obviously going to be positive. And then that x minus 1 is also going to be positive in this case. So that tells us that the function is negative, meaning it must be going toward negative infinity. So what does that look like on the graph? It means that on the right side of that asymptote, the function's going toward negative infinity. Now let's put this together with the stuff that we saw earlier in the problem. So let's just kind of put together all the pieces. It would appear to me then that this has an asymptote at y equals negative 2. Then the function here would be going up to the asymptote and being deflected, and the same would be true over here. Voila. So that's what I would expect to see on the graph. Pretty cool that there was a lot to analyze. There was the limit as x approaches positive and negative infinity. We noticed that there were also a couple of asymptotes, so those are 2 one-sided limits, and 1 actual computation. So hopefully this has been helpful for you guys. Best of luck with it.